Okay, so let's jump into the structure of this code. Starting from first, we have this parameter set, which basically has all the information and all the configurations and hyperparameters that our network is going to be trained with, including the layers, which are the numbers in linear terms. So this means that there's going to be 2 hidden layers, each one with 30 neurons. I can change this to 300. So the first layer is going to have 300 neurons, and then the second one is going to have 30, and we can add this list as arbitrarily as you want. Then we have the learning rate, the dropout, and the L2 lambda. This is the lambda, the L2 regularization constant. And then we have the batch sizes that is going to be used for training, the number of training points, and the number of dev points and test points that needs to be generated. And then we have the number of epochs, activation layer, which optimizer to use to train the network. The loss function, which because this is a regression task, we're going to use the MSE or mean square error loss. The function name that we are going to have a few functions that we're going to try, and I will show them shortly in the lower sections of the code. And then the function that we want to estimate, we have to specify the upper and lower bound of the domain, and then the device that we want to train on. So this is going to be CPU 0 in case that we want to train on the CPU. If you want to train it on the GPU, the value is going to be CUDA :0. So this hyperparameter set class is going to have a method called create optimizer, which is going to take this string value here and create a PyTorch optimizer depending on the type specified. And then there is this helper method called duplicate, which is going to take one hyperparameter set and is going to copy it into a new one so that we can change it as we're going to compare the different changes in the hyperparameters and its effect on the trained neural network. Next to that, we have the actual neural network model, which is this class function approximator network, which extends from nn.module, which is a class implemented in the PyTorch library. With every classes derivating from this nn.module, you're going to have a constructor here, which is going to basically set up the network, and then you have this forward method that will tell how your network is structured. So to break down how this one works, this HPS here is going to be an instance of this hyperparameter set class that we just explained. So it's going to create the layers of the network here. This last dimension here is the size of our input, which is 1 because it's just a simple function. And then for each one of the layers specified in that hyperparameter set layers, it's going to create a linear layer here, which the last dimension is going to be the input count, and then the layer is going to be the number specified in that array. And then we're going to use this set attribute method and set an attribute into the network here. And the reason why we implemented it this way is that we want to try with different network architecture and different layer neurons in each layer. So this will give us a flexibility of, instead of coming here and changing the actual structure of the network, we can only specify the number of neurons that we want here, and everything is going to be taken care of here. So it's going to iterate over the layers and the neuron count in each one of the layer, and it's going to set an attribute. What gives this flexibility that we want is that the set attribute is going to take a string as the name, so we can easily add a prefix and then an index to the layer that we want. And next, because this layer is going to be connected to the next layer and each layer requires an input and output count, we're going to set the last dimension as the number of neurons into this one. So with this for loop, each one of the layers is going to be connected to each other. And then we create the output layer, which is itself a linear layer again. And then because we're going to need this hyperparameter set, we're going to keep this in that class. So the forward method is going to basically glue all these layers together and get the result that we expect from the neural net. So the number of points is going to be the length of our input, which is basically the batch size. And then we're going to we're going to change the shape of this view. You can later on see how this works with the debugger. And then for each one of the layer, we're going to get that layer that we have instantiated here in the constructor. And then we're going to use, we're going to apply X to this layer. So after we get the values, the output values of this layer, we're going to apply the activation function, and if we choose so, we can also apply the dropout to prevent overfitting. And then at the end, we're going to take this X, which is the result of all the input being propagated toward the network, and we're going to apply our output layer to get the final result. So that was the NN module and the core class that is the actual neural network. We have this function, this utility function here, toDevice, which is going to take a data and it's going to transfer it into the device, because we're going to train both on the GPU and the CPU, and we're going to compare those. And this method will copy the data that we want to work with, either to the CPU's memory or to the GPU's memory, depending on which one of the devices that we choose. So next up, let's start with the main function. I guess it's going to be easier to understand. So in the main function, the train network, we're going to take one a list of hyperparameter sets, and the reason that we take a list is that because we want to compare the results, so it's going to take a list. We're going to keep the models and the test data, and then we're going to just start taking the time just to know how long it's going to take. And then for each one of the hyperparameters set into the list that was provided, we're going to create a train, dev, and test data, and we're going to see here shortly. And then we're going to create a model. We're going to print the model to see how it works, and we're going to transfer that model into the memory of the device that we actually want to train on. Then we're going to train the model. We're going to save the model and the test data because we're going to plot them later on. So let's start first with the create data set, which is a very simple 2D function generator. So we're going to take the upper bound and the lower bound, and then for each one of these, we're going to create the data for each one of the sets with this form that we have the number of points and we have the data specs and the function name. So we're going to create the X as a linear space between the lower bound and the upper bound with the number of points. And then we're going to apply the function here. So the function, we have created a few functions here to just test on. So the sine of x, 20 times the sine of x, the sine of 6x, sine of 6x divided by 6, and e to the power of x multiplied by the sine, and also the floor of x, which are going to be test functions that we are going to use here. So let's go back to how we're going to train the model. So when training the model, we're going to first create an list of the indexes of the train set and the def set, because this is going to be used for batching, for splitting the data set into batches. And we're going to see that shortly. So we have our loss function, which is specified into the hyperparameter set. We create our optimizer, which is going to be used for the backpropagation algorithm. Here we have the train loss. Train pointers are going to be information that is going to be printed into the console, so that we can have an idea of how our network is training before getting the charts at the end. So for each one of the epochs, we're going to set the model into train mode. And this is important because some of the optimizer, like the Atom optimizer, is going to track the values into the model. So you have to set that into train mode. And then when we want to evaluate that on the dev set, we're going to have to set it back to model.eval. So we're going to shuffle our train list, which was the list of all the indexes of the train set. And then for each one of we're going to calculate how many batch sizes we have into this epoch, and then iterate over those with this range function here. And at each point, we're going to slice the part of the train data set based on the train list. So we're going to train a batch, and then we're going to add these values and then print them out. To have an idea of how things are going. And then after an epoch is trained, we go back to model.eval to put it in an evaluation mode. And then we're going to use the same train batch to calculate the loss and the point, and we're going to print out the result of the epoch. So let's go to train batch. Then train batch here, model.zeroGrad is going to, it's actually very important to do that because it's going to reset all the informations that the optimizer is going to use for this batch. So it's important to keep that in mind. Then endpoint is going to be the length of the index list. And for each one of them, we're going to add the inputs to this array. And then we're going to convert them into a PyTorch tensor here. So that we can use those, we can pass those as a model into the model when training. And finally, we have to move them to the device that we actually want to train on. So this is important to keep that in mind. If you are not using a GPU, this code without the two device will work fine. And then when you save the model, as soon as you load it on another computer, it is going to work fine because every computer basically has a CPU. But if you train your model on GPU and then you open it on another computer that doesn't have a GPU, then your model is going to fail because it expects to be transferred into the CUDA device that you have specified at the top here, whereas if it doesn't exist on that computer, it's going to give you an error failing to load it. So let's continue. We have our input and our target created as tensors. We're going to calculate the output of the neural net, and then we can use our loss function here to get the loss of each one of the items in the batch, and then we can use this loss to do the back propagation algorithm, and then the optimizer, using the optimizer, and then do a step. Some of the optimizer, like the Atom optimizer, requires this step because they have to be noticed that the batch has been completed. And then we're going to return the actual loss and the number of points that has been processed, which is going to be later on used to print the result of each one of the epochs here. So let's make a simple run of it to see how this actually works. So I have here two different functions that I want to train and then to compare the result. So one of them is the sine of x, and the other one is the 20 times sine of x. And then I'm going to give them all to this train networks to see how the result is going to look. So let's run the code. So as you can see here, it's printing the loss of the epochs. And then the second network is going to start training. And then here are the results. So the first one is the sine of x, and the second one is 20 times the sine of x. So next, now that we have a little bit understanding how this code works, Let's go to the exciting part to try different hyperparameter set and the effect that they're going to have on the trained model.